Think fast. Which would you rather have? 4 toys and 3 snacks, or 6 toys and 2 snacks? Would you be willing to give up your animal crackers if it means that you could enjoy the dinosaur pistol and the bunny bowl? Which would you rather have? 4 and 3, or 6 and 2? Maybe this is hard to figure out real quickly. Maybe it isn't. Maybe you'd just as soon have one as the other. We're now going to explore a tool that economists use to represent consumer preferences. This tool is called the indifference curve, and it becomes part of a map that represents all the combinations of goods that you find more, less, or equally desirable. Once we've drawn a map of indifference curves, we can put the indifference curves together with the budget constraint and derive the consumer's demand curve. That is, once we know what your constraints are and what your preferences are, we can use them together to predict your behavior. So let's get right to it. How do we draw an indifference curve? An indifference curve is defined as a set of points representing combinations of 2 goods, like toys and snacks, that a consumer finds equally desirable or equally satisfying. So we have to begin with a list that the consumer provides us that tells us those combinations that he or she finds equally desirable. Suppose we have a consumer named Chris, and we quiz Chris about toys and snacks, and he provides us with this list. This list tells us that Chris would just as soon have 2 toys and 6 snacks as 12 toys and 1 snack, or 4 toys and 3 snacks, or 6 toys and 2. All of the combinations represented on this table provide Chris with an equal amount of satisfaction. That is, Chris is indifferent among each of these alternatives. He'd just as soon have this one as this one or this one. Let's represent now Chris's preferences in a graph. Here we are back in goods space, and let's remember to label our axes. That's always important. The vertical axis is going to represent the number of snacks that Chris has, and the horizontal axis, just like before, is going to represent the number of toys that Chris has. Now let's take the information from the table and represent it in the picture. So we'll start with the combination of 2 toys and 6 snacks, and that will represent with this red dot right here. Next, we find the combination of 4 toys and 3 snacks equally satisfying, so we can put that point right here. Then 6 toys and 2 snacks gives us this point, and finally 12 toys and 1 snack gives us this point. All of these points represent combinations of snacks and toys. And all of these points, according to Chris's report, provide him with an equal amount of satisfaction. Now, you can imagine that there are a lot of other combinations in between these dots that represent combinations of toys and snacks that Chris finds just as satisfying. We can represent these infinite possibilities by connecting the dots and drawing a curved line that we call an indifference curve. So here I go, connecting the dots. And there's my indifference curve, a collection of points representing combinations of snacks and toys, all of which Chris finds equally satisfying. Looking at this indifference curve, you'll notice I drew it pretty carefully. I'm trying to make sure that the way I draw the indifference curve is consistent with what economists believe about people's preferences. Let me be specific. The first thing you'll notice about this indifference curve is that it's downward sloping. The downward sloping indifference curve means that both of these goods are desirable. That is, if we take away some of Chris's snacks, the only way that we can leave him just as happy as he was before is to give him some extra toys. Anytime we take away one of the goods, we have to compensate by increasing the quantity of the other. and that gives us a downward sloping indifference curve. Every time we lower snacks, we have to increase toys. It's another way of saying that more is better. If we had a combination of toys and snacks that represented an increase in both, well, Chris would prefer that, so it would have to be on another indifference curve with another set of combinations. For instance, suppose we consider a point like 2 for 6 snacks and 2 for 6 toys. Since that represents more toys and more snacks together than any of these points in here, that would be a point that would be way out here on another indifference curve somewhere. So a point that has more of both goods than a point on this curve would be more satisfying, and therefore it would lie on another curve somewhere, a curve that represents increased satisfaction. Another thing to notice is I've drawn this curve sagging downwards. We would call this a convex curve because it's bowed downwards towards the origin. A convex curve is a curve that has a decreasing slope as you move down it. Notice up here the slope is very steep. Then the slope gets a little flatter, and finally down here towards the bottom, the slope of the curve is very flat. Now you'll recall from our early math review that the way you find the slope of a curved line is to take the slope of a line that's tangent to the curve. So for instance, if we want to know the slope of this indifference curve at this particular point with 4 toys and 3 snacks, we would look for the straight line that is tangent to or touches the curve at that point. And that tangent line's slope is the slope of the indifference curve at that particular point. Notice that the slope of the tangent line as we move down the indifference curve is getting flatter. The slope is decreasing. The line is getting flatter as we move down the curve. Well, that's just a mathematical statement about what convexity means. But actually, this convexity has an economic interpretation. Notice that when you're way, way up here, whenever Chris has a lot of snacks and very few toys, the curve is steep. That means if we take away a lot of Chris's snacks, we only have to give him a few toys to compensate. Or to put it another way, if we take away one of his precious toys way up here, we have to get him a whole lot of snacks to leave him as happy as he was before. Just one toy less means a whole lot more snacks to leave him at the same level of satisfaction. Whereas if you're down at a point like this, and you take away one of his toys, you hardly have to give him any snacks at all to compensate. You can take away a toy with very little compensation because he has lots of toys. The slope of an indifference curve is called the marginal rate of substitution. And the marginal rate of substitution will be different as we move along the indifference curve. Up here, where the slope is steep, the marginal rate of substitution between snacks and toys is very large. If I take away one of your toys, I have to give you a lot of snacks to compensate. The marginal rate of substitution tells you how many snacks you would require in exchange for one toy. As we move down the curve, the marginal rate of substitution gets smaller and smaller and smaller. When we get way down here, where the curve is flat, the marginal rate of substitution is very small, which means if I take away one of your toys, that I don't have to give you very much snack at all to compensate you. That's because you've got a lot of toys. They're not as valuable to you in terms of snacks. So, a quick summary. The indifference curve slopes downward to represent the fact that both goods are desirable, and that you have to have more of one to compensate you for a loss of the other. Also, if you have more of both goods, you'll move up to a higher curve somewhere else, somewhere up here to the northeast. Finally, the slope of the indifference curve is called the marginal rate of substitution. And it's like a kind of internal price, a psychological price that you put on toys. If the marginal rate of substitution is big, then you want a lot of snacks to compensate you for the loss of a toy. Your price of toys in terms of snacks is high. But if you move down the curve and the marginal rate of substitution is small, then the price of toys for you in terms of snacks is small. That is, you're willing to give up a toy with very little compensation, with very little extra snack in return. This indifference curve, then, represents a set of combinations that Chris finds equally desirable. Well, let's look at another set of combinations that Chris finds equally desirable, but a set of combinations that provides him with more satisfaction than the combinations on this curve. Here's another table that represents a set of indifferent points for Chris. Chris would just as soon have 2 toys and 12 snacks as 4 toys and 6 snacks, 8 and 3, or 12 and 2. Now, all of these combinations are more desirable than the combinations on our original curve. How do you know that? You know that because right here we have a point that represents 12 toys and 1 snack. On this new list, we have the point 12 toys and 2 snacks. Since this involves more snacks and no fewer toys, that is, it's got more than the original bundle, it must be more satisfying because of our assumption more is better. Anytime you're moving to the northeast, directly to the north, directly to the east, or to the northeast in this diagram, you're moving to points that are strictly preferable, points and combinations that are strictly better. So let's go in and draw the picture that represents the combinations in this graph. Let's start with 2 toys and 12 snacks. That is, 2 toys and 12 snacks will take us up to this point. 4 toys and 6 snacks will take us to this point. And 8 toys, 2, 4, 6, 8 toys and 3 snacks will take us to this point. And finally, 12 toys and 2 snacks will take us to this point. Again, these are only a few of the combinations that provide Chris with this new higher level of satisfaction. If we connect these dots, we'll get a new indifference curve. Da, 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 da. Bam! All of these points are equally desirable. And all of these points are strictly more desirable than the points on the old indifference curve, since it's to the northeast, and more is better. Well, now that we've got a couple of indifference curves, we're going to need some labels to keep them straight. So let's call this original curve U0. U0 represents a number, and that number means the amount of satisfaction you get. We could call that utility. Utility is an economic term that means the amount of satisfaction that a consumer gets from consuming a bundle of goods. So U0 is the original level of utility or satisfaction, and we can label this new higher curve U1, which represents a higher level of satisfaction. Now notice I didn't put in numbers like 10 or 20 or 100 because, what would that mean? Numbers of utility. Measuring warm, fuzzy feelings in numbers. How do you do that? All I'm telling you is that however we measure satisfaction, the points on this curve represent a higher level of satisfaction than the points on this curve. One more thing to say about these indifference curves. Notice there are still points out there to connect with other bundles that are equally satisfying. I could spend all day drawing indifference curves, and these indifference curves would eventually fill up this graph. Indifference curves are everywhere dense. Every point on this graph has some other points that are equally satisfying, and I could spend all day drawing the lines connecting them. I would eventually have an indifference map, a complete representation of Chris's preferences. What can we say about this indifference map? We can say a couple of things. The first thing we can say is that the curves are everywhere dense. Everywhere you put your pencil in this graph, you are touching an indifference curve. The next thing we can say is that indifference curves can have all kinds of shapes. They don't have to be concentric circles. These indifference curves can be kind of weird blobby things as long as they're downward sloping and as long as the slope decreases as we move down the curve. One final thing. Indifference curves can never, ever cross. Can you figure out why? I'll give you a hint. Remember, more is better. Let me show you. Suppose we had a situation up here where an indifference curve like this crossed over another indifference curve at a point like this. Now, how do we know that something like this can't happen? Well, we know from the following argument. Let's say we've got 3 points on this particular indifference curve, and we'll call them A, B, and C. Now let's take a couple of points that are on the other curve, and we'll call those points D and E. Now the thing that I want you to notice here is that point B is on both curves. That's what it means for the curve to cross. Well, according to this logic, D is northeast of A, that is, D has more stuff than A, so that must mean what? That's right, D is better than A. On the other hand, if you go down here, you'll see that since C is to the northeast of E, that must mean that this bundle, which has more stuff, is better. C is better than E. Well, if D is better than A, and C is better than E, we have a contradiction, because A is just as good as B, which is just as good as C. And if C is better than E, then A must, by transitivity, be better than E. However, we've already said that E is just as well liked as B, which is just as well liked as D. That's what it means for them to be on an indifference curve. Hold on. If A is better than E, and D is as good as E but better than A, then we've got a mess. We've got some kind of contradiction. How can A be better than E and worse than D, which is the same as E? It doesn't make any sense. It is illogical for these indifference curves to cross. You can't have more is better and have crossing indifference curves. So we'll put a big circle slash through this. This is not a possibility. Indifference curves never cross. Well, we've done a lot in this lecture. We've taken a set of preferences that Chris expressed, and we've represented them in a curve called an indifference curve, a collection of points that represent equally well-liked combinations of two goods. Then we saw that that indifference curve slopes downward, has a slope that represents a kind of psychological price called the marginal rate of substitution, and we saw that this indifference curve is part of a big indifference map that represents Chris's preferences for toys and snacks. Now, we're going to use this indifference curve along with the budget constraint to make some predictions about Chris's behavior, and eventually we'll be able to derive Chris's demand curve.